So good morning, everyone. Uh, these two topics, basically Dijkstra and Bellman-Ford. So how many of you are aware of these two? Nice. Most of you. Right. Yeah. So these two topics in general are like quite big. So they take around 1.5 lecture each for uh, this like Bellman-Ford and Dijkstra, but we don't have much time. So I won't get into the proof of how things work, even for the correctness. So Dijkstra is a pretty intuitive algorithm. It's a pretty easy algorithm, not intuitive, but the correctness is not that intuitive. So for that, I'll just tell you that what are the things they have used for the correctness proof, but I won't get into in depth of each and every proof. So I'll start with A star. So this is one of the visualization I got from GitHub. So I've linked the link over there. So this is what how A star works. That you have a heuristic, you have a start and goal, and you can see that I have used multiple heuristics over here, including Octile and Chebyshev. And you can see that with a heuristic, it is quite optimal in that sense and efficient, I would say. But the thing is that in most of the case, not most of the cases, but there are cases where where you don't have heuristic or where you don't know how to actually define the heuristic. Secondly, that for multiple short, like if you want to get to know the shortest path of multiple nodes, A star kind of falters over there because you for heuristic you have a goal node already set. But if you want to know shortest path for each and every node, for that you cannot use A star or you'll have to make changes to A star. So for that case, Dijkstra, we use Dijkstra algorithm over there. So it's a very basic single source shortest path problem. And then there are a lot of algorithms, a lot of works which has gone into speeding up Dijkstra, but this is one of the more basic Dijkstra algorithm. This is the basic Dijkstra algorithm. So we'll start with what exactly is shortest path. So shortest path is basically you take the minimum of all the possible paths from source to any destination. But can anyone tell me why this particular definition, this first line, mathematically is wrong? Like purely mathematically like rigorous. It's not a good definition, I would say, in terms of graphs. Uh, yeah. Marker. We don't have marker, right? Around. So okay, I don't have that. So imagine that why this is like not exactly correct. That you have a negative cycle. If you have a negative cycle, this shortest path can basically become negative infinity because you'll just keep on going on that cycle, and that cycle, and then and if that particular destination is reachable from the source, then your shortest path basically becomes negative infinity. So you won't use minimum, you'll use infimum over there. So that's like basic slide change. But from here, what we'll start is like one of our basic assumption for Dijkstra would be that there will be no negative edge and so basically no negative cycle. So weight is if you go from one node to another, the path will increase. So and the two preliminary concept for the Dijkstra kind of piggybacks on is DAG relaxation. So I'm not sure. Are you guys aware of DAG relaxation or DAG in general? Acyclic graphs. Okay, we'll just go into relaxation. What relaxation means is that if if you can reach a node from a previous node and the previous weight was lower than the new weight, was greater than the new weight, then you relax the node. And relax basically means that you give the new weight to that. And second, very basic proof, very important proof is, and I won't get into that, is relaxation is safe. What we mean by that is that what whenever we relax that edge weight, the node weight, it will always be some sort of path weight to that. As in, if you go from some path, only that particular weight will be assigned to it. That is what we mean from relaxation is safe. And another like kind of the consequence of that is that the after relaxation, uh, it will never be lower than the shortest path. So after you relax a node, it will never be lower than the shortest path available to that node. So it can be equal. There could be multiple shortest paths, but it will never be basically lower than that. So that is one thing which we go with. And the second is basic triangle inequality. Triangle inequality, I think everybody is aware of, right? Yeah. So, okay. So Dijkstra algorithm is a mixture of BFS and DFS. So as I said that most of the algorithms kind of works with BFS and DFS. BFS mostly. So what it does is that when you go to a node, you kind of explore every single possible vertex, that is every neighbor. But it is greedy nature as well, that you explore everyone, and then the next node you go to is the lowest weight one. So that is what Dijkstra algorithm is. So, okay. Another thing is, which I've already told you, that since weight is always greater than 0, then and if you are crossing one part to the other, like if you are taking one node to reach the other node in a shortest path, then the shortest path of the previous node would be lower than the shortest path of the next node because the weight is greater. Yeah, that's it. And that relaxation is fine. And the third one is, and here comes something which is quite important for data structures, is what kind of data structure should you use to optimize this Dijkstra algorithm. So Dijkstra, if you find out in like theoretically has a time complexity, but if you use something like an array or something, then you won't be able to reach that time complexity. So that is something that is very data structure thing, and I'll just tell you what kind of data structure gives what time complexity, but I won't get into what is that data structure. Okay. So, okay, I'll start with what exactly Dijkstra algorithm is. The pseudocode is very small, and this is what exactly Dijkstra algorithm is. So, as I said earlier, it's a pretty easy algorithm. It's not that difficult at all. And I'll also give one demonstration of how it works. So, what we do is we just for the source we give the distance as we assign the distance as 0. And for rest of the vertices which are not source will be assigned infinite. And then we like initially the visited node will be 5 because we have not null because we have not visited any node by any vertex by then. And then we use a changeable priority queue as our data structure. So in that we first build the queue, and we give all the vertices to that queue. And then we start our entire loop runs that until and unless the queue is null, as in all the nodes have been removed from the queue, we'll keep on going in the loop. And for each and every and in that every single time we'll find out the minimum distance of that queue. In the queue which has the minimum weight, we'll explore all the neighbors of that particular vertex. And then for that, we'll relax each and every vertex neighbors. So this is how the pseudocode works. I'm pretty sure it was not that apparent what I just said. So I'll first give you an example. So this is one of the graphs. So you can see that there are basically 5 vertices, and there are multiple edges over here. And we have, yeah, sorry. So we have built a, yeah. So we started with, we'll first assign the distance of source. Our source is A. We'll first define our distance of our source as 0. So we did that, as you can see in the priority queue. I should. Yeah. So you can see that the distance has been assigned as 0 for the source. And for the rest of them, it's infinite for now. Then our visited node is null, and our priority queue is A, B, C, D, E for now. All the vertices. Then we'll get into the loop. Since it's not null, we'll find the one which has the minimum distance. which is for now A. So we chose A for now. We chose A. Now, what are the neighbors of A from here? B and C. So we'll relax B and C now. So if you relax B and C, the earlier the weight of B was infinite as well as C had an infinite weight. But now you can see 0 plus 10. 0 is the shortest distance of A to A, and the weight of A to B is 10. So shortest distance of the previous node plus the weight, which is 10. So 10 is less than infinite, and as well as 3 is less than infinite. So our visited node becomes A, and the weight has been updated. The weight in the priority queue has been updated to 10 and 3, as you can see in the example. Now we again go back to our initial loop, the loop condition. So now that A has been removed, we have B, C, D, E left. Now in the B, C, D, and E, the minimum weight is of C. So we'll now explore C. And what are the neighbors of C? D and E. So what will be the D? So now we'll relax D and E's weight. So what will be the new weight of D and what will be the new weight of E? Exactly, 11 and 5, right? So now C has become a visited node, and the new weights have for the priority queue has become 7, 11, and 5. Now again we'll go back to our loop condition. So now three vertices are remaining, B, D, and E, and the lowest weight is of E. So we'll now go to E, and what is one neighbor of E? That is D. But if you add 5 plus 9, that becomes 14. So you won't relax here because it doesn't meet the relaxation criteria. Yeah, we have 24 minutes. Okay. So it doesn't meet the relaxation criteria. So we'll go back to, sorry. Oh, okay. Sorry. Thanks. So now we'll remove E. Similarly, now there are two vertices remaining. One is B and one is D. We'll go again through the same thing again. And finally, this will be our shortest path, ACEBD. This is the shortest path we'll go. And these are these are the weights, like the shortest path weight, how you can reach over to each and every vertex. So, sorry? Sorry? A, C. No. So it's not the shortest path for each. So if you reach over here, so if you want to go for B, so that will be ACB, right? So one thing over here is that what A star didn't do was that A star just gave you the shortest path till that particular destination. But here you can find that for each and every vertex, you could find the shortest path, right? And the shortest path is available to you. So again, I just gave you how this Dijkstra algorithm works. But now comes the point where how is this correct? How does it even make sense? Because it seems pretty easy, but how does this algorithm even make sense? So again, I won't get into the details of how the correctness proof works, but it is pretty easy and you can find it all over the internet. But there are three things on which it works on, and one is optimal substructure property or subpath optimality. Are you guys aware of that? So basically what it means is that if you have a subpath, if you have a path which is optimal, then if you go to a subpath, that also will be optimal. So this is what it is based on. Second, relaxation is safe, which I've already told what it means. But again, the proof of that is something that you can go and find on internet. And third is non-negative weight, which is basically the premise of the entire Dijkstra algorithm. So again, so this was the correctness part. Again, I'm sorry that I couldn't explain. We don't have enough time for that. Now we'll come to the running time or the implementation. So the entire implementation was based on the changeable priority queue. So that defines how the running time of your algorithm. So basically we use three. One is array, binary heap, and Fibonacci heap. Okay, so we'll come back to here, pseudocode. So, okay, while q is not equal to, so can anyone tell me not exact time complexity, but what will be the time complexity of this pseudocode? Sorry, b plus? No, so one thing is for sure that this particular thing runs for entire vertex. And then there is one which is inside that, which is running for all the edges. So very into E would be there. Huh? Yeah. Yeah. There will be one thing which will be based on the square of that. 1 second. Yeah. Okay. Yeah. So, so first thing is that this entire loop works works for the entire like total number of vertices. Second is inside that there are all the edges. So you have to traverse through all the edges over there. And third is you have to do the deletion operation, which we were doing. So these are the three major things that it works on. So if we, it depends on the type of like priority queue we use. So it's array, binary heap, or Fibonacci heap. So for all these cases, for the building operation takes n time. So we can just remove that. That is already uh, sorry, single order. The second thing is delete min. So the minimum delete min operation. So that will take n time. N is basically the number of vertices. So if we use array and the updation step takes constant time. So this will become n time, this particular operation. So number of vertices into number of vertices, which becomes second order, OV square. So that's fine. That's the second order. Second comes to binary heap. Again, the delete min operation becomes log NA, so log number of vertices, and the decrease key again is a logarithm. So why logarithm is better? So imagine that if you have a second order, like if you have v square and you have 10 to the power 60 vertices, so that becomes 10 to the power 120, right? But for if we use log, that becomes 60, right? So it's pretty low in that sense. So if you use that, it's a very simple procedure to find the time complexity. You'll come with e plus v log v, e plus v log v. So we now why they have used e over here, it's important because imagine that you have if you have let's say dense graph. So if you have a completely dense graph, what will be the number of edges? Completely dense graph as in each vertex is connected to the other vertex. Sorry? NC2, right? Exactly. So n into n minus 1, basically n square. So e plus v log v again is very high. Like you have n square over there. N into n minus 1 by 2. And then comes Fibonacci heap. So Fibonacci heap, what it does is even the decrease key operation is constant. So that turns out to be e plus v log v. So this is the most efficient one. But if you actually go for implementation and if you look for like in Geek for Geeks and everything, people use binary heap and array only for sparse graphs. Because theoretically, Dijkstra gives e plus v log v, but generally you use the first two for like actual implementation. So I'll just show you one of the implementation. So you already saw how A star works, right? This is how Dijkstra works. Sorry, where did that go? Yeah. Yeah. Don't know why this is not. Yeah. So Dijkstra kind of creates a frontier. You can see that it is going like this. So without heuristic, if you have a heuristic, you don't necessarily need to go for Dijkstra. If you have a admissible and consistent, if I'm not wrong, heuristic, then you can go with A star, because A star will be much more efficient in that sense. But if you don't, and if you have other requirement, as in like you need to explore, you need to know shortest path for each and every node, then you can actually work with Dijkstra. But because Dijkstra kind of explore, it creates a frontier and then it keeps on exploring everything. But A star works with a heuristic that, okay, this is the Chebyshev or this is the Euclidean distance and we have to go there. So, okay. So yeah, this was it. Kind of rushed. I'm sorry. We have 15 more minutes. Nice. So, okay, we'll come back. We'll start with Bellman-Ford now. So we already had, yeah. Hmm. Exactly. So it creates a frontier at every step. So that's what I said, that if you have a heuristic, then it's better to go with A star. Dijkstra, A star is more specific version of Dijkstra, you would say. You have a heuristic. You know how to go, you know where the goal is. But in Dijkstra, you don't have that information. So you're just kind of exploring everything. So that's why there is a guaranteed exploration in Dijkstra. So it depends on what your requirement is. If you want that sense, then in Dijkstra is better for you. If you don't have a heuristic, you don't know how to define heuristic, then Dijkstra is better. But in general, Dijkstra is better. But if you have a heuristic in mind, then yeah, go for A star. It will be much faster. Ah, sorry.
Dijkstra we consider the blind search because it's not provided.
Yeah, it's kind of uninformed. Yeah, you don't have the like idea of where that is. Yeah. Sorry. Yeah. That's why I can't hear you. What? Yeah. So okay. So this is the data structure that you're using. Is my cursor visible by any chance? Yeah. It's not better then. Yeah. So this Q, letter Q, is the data structure that you're using. So first you have to build this. So you are giving all the vertex to that. So that's the build operation. Do you min distance? When you find the minimum distance, you first give that to, like, you assign that to the visited node, but that's not the part of it. You remove that key from the queue, because this is the condition, right? While q is not equal to 5, if you have not visited every single vertex, then deletion is one operation. And you're relaxing it. Relaxing, you are updating key of each and every element of the priority queue. So that is the third operation. So these are the three operations that you're performing. Okay, this one. Yeah. So first, in this is the case where you're building the entire queue. Okay. So after A, you see the one which has which is more transparent. A, that transparent blue. So that means that we have removed that from the queue now, because we already have visited that and we know the shortest path of that. So we remove that from the queue. That is a deletion operation. And now you see that in the queue, we change the weight from infinite to 10 and 3. That's, you are updating the key. So that is the updation operation. So these are the three operations that we are performing. Yeah. So priority queue, you have weights for it, right? So that is the weight which you are updating. So these are the three things which you are doing. Okay, we have time. So does anyone have any question? Pretty sure you'll have, but yeah, what can we do? Okay, so we'll come to Bellman-Ford. So now Bellman-Ford is the most general algorithm, and this is where we kind of deal with the nemesis, I would say, that we had negative edge weights and negative cycle. Okay, so I've already told you that if exists, then the shortest path should be something like infimum. But again, if you have a negative cycle, you necessarily don't have a shortest path. So you want to have you want an algorithm which tells you that if there is a shortest path available, as in if there is a negative cycle, you don't have a shortest path, right? So you need an algorithm that tells you that if there is a negative cycle in the graph, one, and if there's not, then you should get the shortest path. So this is what Bellman-Ford does. So are you guys aware of simple paths? Yeah, simple paths. Okay, so what simple path means that the shortest path only visits any vertex once. Okay, so if you have, let's say, seven vertex, so the shortest path could be 1, 2, 3, 4, 5, 6, 7, but it can't go beyond that. Okay, and what does that mean? Like, why is it true? Any idea? Like, it's pretty intuitive, I would say. Yeah, so like just think about it. Sorry. Yeah, exactly. So if you have, let's say you have A, B, and C, and B has a cycle around, let's say, and the shortest path you're getting is A, B, C. The shortest path you're getting is A, B, then cycle around B, and then C, something like that. So if that is not the shortest path, then basically means that if you go again through that cycle, you'll get another shorter path and another shorter path and shorter path. So basically there is a cycle. And if the weight is greater than 0, then that won't be a shortest path, because if you go around that cycle, weight will increase. But then there is one edge case that if the weight is 0, then you can just keep on going and you can just coalesce that entire thing into one node. So it doesn't matter. So basically, there exists a shortest path which is simple. You can have multiple shortest paths which are 0 cycles and other things, but there exists a shortest path that is simple. So that is the case. And if you have a shortest path, that means that you will have at most v vertices. And if you have at most v vertices, how many edges will you have? V minus 1, right? So that is basically the entire premise of Bellman-Ford. And there's a very strong statement that, and there are intricacies to it, but the overall sentiment is that if you have a if you have a path where you have visited V edges, and the shortest path you got from visiting V edges is smaller than the one which you got from V minus 1 edges, then basically the shortest path will be negative infinity. Again, so what I said earlier, that if you have already visited V minus 1 edges and you got a shortest path over there, let's say that is X, then you again went through one of the edges, you added one more edge to it, then and the shortest path basically came out even smaller than that, then that tells you that the shortest path to that particular destination will be negative infinity. And that comes from the simple path thing only. So it's not a yay. But again, there is a proof to it. I won't go into it, but it's available all over the internet. But this is one of the strongest statements that Bellman-Ford works on. Okay, so I'll come to the algorithm now. We have 7 minutes. Okay. So Bellman-Ford works on graph duplication. So graph duplication means that if you have like you duplicate the graph, and then at each and every duplicated graph, like at the kth instance, how many edges have you traversed to reach there? That is what is meant by the kth graph that you have duplicated. So I'll tell you, I'll show you via demonstration, but this is the pseudocode of Bellman-Ford. So Bellman-Ford is that first you initialize the final distance to everyone. Then you run this entire thing for v minus 1 times. So it again comes to the simple path thing, that we'll first run this entire thing for v minus 1 edges, v minus 1 times. So we duplicate the graph v minus 1 times. And then we relax each and every edge once. And then this loop kind of goes on and on for v minus 1 times. And then after that, we run it one final time. And if the new distances are lower than the older distance, that means that there exists a negative cycle. So this is how Bellman-Ford works. Okay. And again, relaxation is the same thing which has been mentioned. Okay. So this is one of the graphs. Okay. So you can see how many graphs are, how many vertices are over there, are over here. 5, right? So basically we'll just duplicate it 4 times and then we'll see the order. But okay, I have a better demonstration for this. So this is the graph for now. So this animation I've taken from TUM. So it's available on internet. Just you can write TUM Bellman-Ford animation. You'll find it. It's pretty intuitive as well. And these are the vertices I have. This is the source node I have taken. This is N1, N2, N3, N4, and N5. Okay. And okay. So I start with my shortest node, which is S over here. I'll work like this only. Okay. So I started with my shortest node. And now first time, this is the order in which I'll examine each and every edge. So first we'll come to this. So we'll run this entire thing. How many vertices do I have here? 1, 2, 3, 4, 5. 6. Okay, sorry. So we'll do it 5 times and we'll relax each and every edge. But I've already determined the order in which each edge will be relaxed. Okay. So we'll start with this. So this is my shortest node. I have source node, which I have defined. And now you can see that the first thing it was initialized. So each node, you can see the first source node has been given 0 and rest of them have been given infinite for now. Now the first order is S to N1. So you can see the red one. We are checking S to N1, which is red. 0 to 33, if you go like that, then the relaxation criteria is met. The infinite has become 33 now. The second one is N2 to N3. But N2 already has infinite. Infinite plus whatever edge weight you have will be infinite. So that relaxation criteria is not met. So it remains infinite. Then you go to N2 to N1. Again, infinite to whatever, it's not met. So that has not been updated. Then goes N1 to N3. Whatever is in red color is the current edge that we are looking at. So N1 to N3 is 33 plus 134, which is less than infinite. So basically we'll update that. So you can see that has become green. And the final thing is 0 to 20 and this S to N2, the red one. And that has become 20. Again, N4 to N2 is will remain. So, okay, one thing before we go. Can you spot something in this particular graph? I think we won't have time to complete this. We only have 3 minutes, so just we'll stop it over here and then we'll do 10 minutes Bellman-Ford tomorrow or on Wednesday. So can you spot something in this graph? Negative edges is fine. Negative edges is fine. I don't think there's negative cycle. Is there a negative cycle? But that's not negative cycle. You see, N2 goes to N1, N1 goes to N3, but N3 doesn't come to N2. N2 goes to N3. So that's not a negative cycle. Sorry? Exactly. N5 and N4 are not reachable. N5 and N4 are not reachable. So basically, after your entire algorithm is done, you should get N5 and N4 as infinite as the output. Right. So, and I don't think there's a negative cycle over here, but I'll in the next class, I'll find something with negative cycle and then we'll work on that. But I don't think we'll have enough time to complete this entire thing. So yeah, okay. It's already 9:50. I'll begin with Bellman-Ford. So Bellman-Ford is the most general algorithm. You can, here we deal with negative edge weight and negative cycles. So like, you don't deal with negative cycles in general. You have negative cycle, and if you have a negative cycle, you basically, and if it is reachable, then basically the minimum path will be negative infinity. So you don't deal with negative cycle, but you just kind of detect if there is a negative cycle. So that is the whole aim of Bellman-Ford. So first you find out the shortest path, and then you check if there's a negative cycle. If there's a negative cycle, then the shortest path goes to infinity, and you just return that there was a negative cycle found. So we were already here that the shortest path is basically becomes infimum if you have a negative cycle, because you just keep on going in that negative cycle, and then your weight will keep on reducing. And we also had this that if delta SV, like basically the shortest distance between a source and a vertex is finite, then the shortest path would be one of the shortest path would be a simple path. And a simple path being that you only cross that any vertex once. So so for any simple path, at most you go for you pass V vertices, and at most you will have V minus one edges. Like, I think that's intuitive. And the more stronger thing was that if after crossing V edges, you find a shorter a path which is shorter than the one after crossing V minus one edges, that basically means that there is a negative cycle, and the shortest path will become negative infinity. Yeah. What is the negative cycle? Okay, I'll show you. I actually came with this today. Huh. Can you find the negative cycle over here? Exactly, TXY, right? Yeah, if you go to TXY, so I'll tell you what. Uh, if you have to go from S to Z, if you have to go to S to Z, then one path would be 7 plus 9, 16. Now one path would be 7, then from S to go to Y, then go to T, then go to X, then go to Y, and then go to Z. So then you'll have negative 1. Now repeat this cycle one infinite times. Basically, your path will become negative infinity because there's a negative cycle. So after you go around that cycle, the net path distance becomes negative 1. Yeah, no, not negative unit. If you add this YTX cycle, yeah, YTX cycle, that's 2 plus 5 minus 8. That's minus 1. Yeah, so SYTXYZ, that becomes negative. So if you go on going in that cycle, YTX, 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 your path will keep on decreasing, and then you'll never find a finite shortest path. Yeah. Yeah. Then there'll be just negative edge. Imagine that, imagine just Y to T was 3. Then that becomes 0. Even if you keep on going in that cycle, it won't alter the weight path, shortest path's weight. So you can just coalesce into one, and again that will be a simple path only. So if you can have a negative edge without having a negative cycle. So if you have 3 plus 5 minus 8, that becomes 0. Now if you keep on going into that cycle, you won't reduce the weight of the shortest path. So yeah, like it doesn't matter. It's still the shortest path would be 16, I guess. Or something. We'll find out. Yeah. Sorry? Huh. Huh. Imagine if it is 1 also. Okay, so then S to Z, if you go from S to Z, taking the path SYZ, then that becomes 8. Okay. Now, and as you said that Y to Z is now 1. So we'll now go via taking that cycle. So now first we'll go 7. First we'll go from S to Y, then to T, then to X, then to Y, then to Z. Okay. That becomes 7 plus 2 plus 5. So minus 8. So that becomes minus 6. and 6 plus 1 is 7. Okay. But now you take the cycle 8 times. Because that will effectively give you the shorter path. No, it's a directed graph. Yeah. No, so here the thing is that you have to find. Oh, yeah, thank you. Here the thing is the aim is to find the shortest path. If you keep on going, not the aim is not to go through the least go through the least number of nodes, but is to go through the like the path which has the shortest weight. So if you keep on going in that txy cycle, then you'll effectively have a weight which will be less than 8, right? Okay, I'll tell you. Imagine that it was not -8, it was -16, something like that. Okay, then if I go in that cycle once, then that becomes 7, 7 minus 9, -2. It directly becomes -2. Then you already have a path which is lesser than that. Am I clear? It doesn't matter that the weight of the cycle matters, the weight of the edge matters. Yeah, weight of the cycle is basically some of the weight of edges, right? Right. Yeah, so okay. What you're saying is that after imagine this is the scenario with y to z with y to z edge weight becoming 1. Okay. So now what you're saying is that after you have gone from y t x cycle, you directly go to z, you don't have another cycle, right? So what you are saying is that 7 plus 6, 6, 7. You got a 7 edge weight, okay? Path weight. But I'm saying that if I again go to that cycle, I'll have a path which will be even shorter than 7, which will be 6. And if I keep on going in that cycle, I'll have a path weight which is lesser than what what your path was suggesting. I can keep on going lower. I can go till minus infinity. If I keep on going in that cycle for like infinite times, my edge weight will become minus infinity, which is lesser than whatever number you are suggesting. Right? Not clear, yeah? Yes, so you'll have adjacency list, right? Okay. So you have at y. Actually, I don't have that. Do we have a marker? Okay, we can use it. That's not to get up, but I'll get it. Right. Okay. Oh, nice. Okay. So, okay. I'll come here. So this, you are saying that this has become 1. This has become 1. So if I go S to Z, S to Z is if I take the path S, Y, Z, then the path becomes 8. Okay. Now I'll have S to Z and I'll take I'll consider this cycle as C. Okay. So I'll take S, Y, C, Z. Okay. So this becomes how much? 7 minus 1 and then 1. Okay, so this becomes 7. So after taking one cycle, my effective weight has reduced for the shortest path from S to Z. Now I'll take S to Z and I'll go from S, Y, and I'll take cycle 2 times. No. So, but my there exists a shorter path. There exists a shorter path from this compared to this. Yeah. So now this will become 6. And what I'm saying is that if I do this like multiple times, like this, if I take S to Z, which is S, Y, N, C, B, and N tends to infinity. this shortest path will tend to infinity, basically. Sorry. Negative infinity. Yeah, that's why it's shortest. But if I go to the cycle again, then why? Sorry, what? I'm going to the cycle. See, I have to go. I'm finding out the shortest path to Z, right? I have to reach. D is my destination. But from once I reach X to Y, then I'm again going to the that cycle of T. You're talking about this point? No, S, Y, T, X, Y, Z. That's the cycle. I'm not going back again. Yes, what I'm saying is that you can go through this cycle once and your path will be reduced. If you go through the cycle infinite times, your effective weight of the shortest path becomes negative infinite. So you just keep on lowering the shortest path. If there exists a negative cycle.
So at any node, I want to find out the what is the total path distance from all possible ways.
Sorry, what?
When I got y, so I want to know how much I can simply go to y to z, or I can go from y to t.
Yeah.
But I want to know what is the total path, all possible ways how I can reach from y to z.
Right.
This is what we want our to do.
No, we want our algorithm to return the shortest path to each vertex.
Do we look to the just the next node or all possible ways how we can go to that node?
Yeah, so we end up looking at okay. That will be in the algorithm that we kind of traverse through all the edges, all the possible edges. And in the like there's another example which I've shown. There are edges which cannot be reached.
This is why this one question is that when I am at y, the shortest path is 1 to z, and the other way is 2. Then I have to go from y to t. That is path length is 2.
Okay, yeah. So
when I am at y, there are two options. That go to t with a path length of 2, or go to z with a path length of 1.
Yeah.
My goal is to go to z.
Right.
And I'm seeing that I can either go to z with a path length of 1 or go to t with a path length of 2.
Okay.
My algo doesn't know that it will encounter a negative path.
Yeah, so we have not gone through the algorithm once, right? We'll go through the algorithm. We'll solve this as well with the algorithm, and then we'll see that how it goes. Okay. Yes. Okay. I hope it's clear now. I don't think it's clear, but okay. So, okay. Thank you. Okay, so now we'll come to the Bellman-Ford algorithm now. So, the algorithm works with initialization. You have source to source distance 0, and the rest of the distances are infinite to begin with. Then, as we have seen that if there exists, if the distance is finite, all we need to do is traverse v minus 1 vertices, right? So, and we have to duplicate our graph v minus 1 times, and we'll relax each and every single edge for all the v minus 1 times for every single time. And then finally, we'll check that after v minus 1 times, for the v8 time, if there exists path which is lower than what we found out with v minus 1. And if there exists a path, then there exists a negative cycle. Okay. And relaxation, the definition is already here. dv is greater than du plus the weight. And then you relax as in you give the new weight to the node. Okay. So for this one, I'll just show you how the graph duplication works. So in this particular case, you can see that how many vertices are there? 5, right? So you have one initialization step, and then you'll duplicate the graph 4 times. And after 4 times, you should if there's a finite weight, if there's no negative cycle, you should essentially get all the shortest weight till there. Okay, so that is the algorithm. I think I should solve this one first because that will be easier for you guys. I'll just copy this 4 times. So how many passes should be there in this case? 4 times, right? Okay. Yeah. I'll solve this one. And then I have one which has animation as well. Okay. So I'll come here. Okay, so now we'll keep our algorithm suggested that we'll have four, like the graph will be duplicated 4 times, and for each time we'll relax every single edge possible. And the order of the edge that will be examined in each case would be this: S to T, S to Y, TX, TY, XY, whatever. Okay. So like we'll do it together. So initially we'll just initialize each and every node. So we'll have infinite over here, 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 here. Okay. So first we'll go for S to T. So S to T is this will be relaxed, right? So this becomes 6. S to Y, this also becomes 7. T to X, where's T? Huh. So T to X becomes 11, right? X to Y, where's X? Oh, huh. 11 minus 8, that becomes 3, right? Y to T. Y to T is 3 plus 2, 5. Y to Z. Where's Y to Z? Y to Z is 3 plus 9, 12. You were able to do everything. And then Z to X. This was 12, right? 12 plus 7, 19. So that won't be relaxed. Okay, so we have traversed all the X one time. Now the second time we'll go S to T again, which is 0 plus 5, 0 plus 6, 5. This won't be relaxed, right? Then S to Y again won't be relaxed, right? Because it's already 3. T to X, where's T? 5 to 5. Again, this will be relaxed. 5 plus 5, 10, right? So this will become 10. X to Y. 10 minus 8, 2. This will also become 2. Y to T. 2 plus 2, 4. This will become 4. Y to Z. 2 plus 9, 11. You can see the pattern that it is getting, everything is getting reduced. So it will eventually, because of the negative cycle. And Z to X. Z to X is 11 plus 7. It won't get relaxed. Now we'll go again. S to T. What is S to T? It won't get relaxed, right? S to Y. This won't get relaxed again. T to X. 4 plus 5, 9. This will get relaxed, right? So this will get relaxed. 4 to 5. X to Y. Yeah, 9 minus 8, but this will also get reduced by 1. Y to T. 1 plus 2, 3. This will also get reduced by 1. And Y to Z. This will become 1 plus 9, 10. Everything in that cycle is basically getting reduced by 1. And Z to X won't get reduced. Again, the final time we'll check. S to T won't get relaxed. S to Y won't get relaxed. T to X. T plus 5, 8. Yeah, this will get relaxed. X to Y will get 0. Y to T 2. Y to Z 0 plus 9, 9. And Z to X. It won't get relaxed. So our Bellman-Ford algorithm says that this should be the shortest path if there is no negative cycle. Okay. Now comes the check step. Now we'll check that if we go for one more traversal, we should not get any shorter path. If there exists a shorter path, that basically means that we have a negative cycle. And there will be a shorter path because you saw, like, you'll see again. This won't be there. This won't get changed. This won't get changed. And T to X. Where's T to X? 2 plus 5, 7. We saw a shorter path. So there exists a negative cycle. So this is how Bellman-Ford algorithm works. Yeah, v minus 1 time we saw, right?
But in the next cycle itself,
Sorry.
in the next cycle itself,
Exactly. That is the thing that the next cycle. Okay, so I'll get back to the proof. The proof where it began, which was this: that if there exists a shorter path after v edges, v traversal, and that is lesser than v minus 1, then there the shortest path becomes negative infinity. Basically, there's a negative cycle. Yeah, so I told you about the simple path thing, right? So there will for simple path, at most you'll have v minus 1 edges, and at most you'll have v vertices. So you're going through v minus 1 edges.
Why did we choose that one? We choose any
Oh.
order?
Yes, sir. Huh.
Why did we choose that specific order?
Okay. Ordering is one thing which again takes like it takes certain time. So we are not getting in the ordering of the edges, but that is the order that was taken in this case. Finding order is also apparently.
That is a different.
Yeah, yeah. Huh.
But here one thing, it will not be a simple path. Because we are visiting the high node.
Yeah, so that is the thing that if there exists a if the shortest distance is finite, then there will be a shortest path that is simple. But since it was not finite, that's why we were it was not a simple path, right? Yeah. So we also assign parents to it at each and every time. We assign parents, like we saw that the minimum distance how we got, and we'll assign parents to it. So we'll in the algorithm we also assign parents to each and every previous node. So it's very easy to find out the shortest path. Okay, I'll show you. It's here. Yeah. So can you see here in the last one? Can you see 2x, 7s, 4y, minus 2t? So minus 2 stands for the weight and t stands for the parents of that node. So if you have to go here, this is a different graph, by the way. To reach z, you have to come via t. To reach t, you have to come via x. To reach x, you have to come via y, and to come to y, you have to reach via s. So you have a parent of each and every node. So to reach a destination, you'll also get the shortest path for each and every vertex, and along with the shortest path that is there. I don't have a good answer to it right now. I'll get back to you on Friday for this. Yeah, I don't have a good answer to this. Yeah. Anything else? Okay, so final is one of the TUM visualization. You can actually find this visualization on internet. You can just search for Bellman-Ford algorithm, and it was from TUM. I actually think that I might have kept this node really low. I'll just go like this. Okay. So again, this is another graph. This is the order of node which is not visible. So you can find it down here. We first go from S to N1. First is that, then N2, N3, then N2, N1, N1, N2, S2, N2. Sorry, that would be N2. N4 to N1, N4 to N2, N5 to source, and then N5 to N4. This is the order of edges that we'll be traversing. Okay. And you can see, so how many iterations should be there in this case? Not for excluding the check. 6, right? Oh, okay, 5. Yeah, nice. Yeah. So in this case, it will just begin, and here you'll find there are edges which are not reachable, nodes which are not reachable. So so initially you search for S to N1, And since it was infinite and the node is reachable, the n1 weight will become 33. Then you go to n2 to n3. That again is infinite. Whatever you do with infinite, it doesn't make sense. So that will remain infinite. The edge won't be relaxed. This again won't be relaxed because the source is infinite. Again, this one will get relaxed because the node is infinite, but the source is 0. So 0 plus 20 is less than that. This won't get relaxed. This won't get relaxed. And this won't get relaxed. So first iteration is done. Now we are going to second iteration. So again, second iteration, n1 won't be relaxed. Now n2 will get, well, n2, n3 edge will get relaxed because 20 minus 2 is 80, which is less than 34. Now 20 minus 20, that becomes 0. So n1 will get relaxed. Then 0, 20 won't get relaxed because that's the same thing again. Infinite till 0 again won't get relaxed because that is here. And now you'll start to see that n4 and n5 are just not reachable from S, if you can see, right? N4 and N5 are not reachable. So by the end of the algorithm, you should get that N4 and N5, the weight is infinite. Okay. So again, we'll go through the same. Now we'll go to iteration 3. This won't get relaxed because this is less than that. Previous one will get relaxed. This won't get relaxed. This won't get relaxed. Sorry, this will get relaxed. N1, N3 will get relaxed because this was 20 minus 2, that was 18. This became 0. So 0 plus 1 is 1. So that will get relaxed. And the others won't get relaxed for this. And basically, we'll keep on going through all these steps. And there will be one final step that iteration 6 basically means the check step. And since we are not getting any like negative cycle, so yeah, these are the shortest ways for that. So yeah, this is the Bellman-Ford algorithm. This is how it works. Now we'll get into the time complexity. And now Dijkstra, what was the time complexity of Dijkstra? That was Gaske bol diya. Huh? So basically V square, second order. But like as the answer is already there, order or like time complexity is V into E. What will be the order of this for dense graphs? Yeah, n cube. Yeah, because if it's really dense, then E becomes NC2, n into n minus 1 by 2. You become n cube. N cube is the algorithm. So in terms of time complexity, it's not a really good graph. I mean, it's not really a good algorithm, but this is a more general algorithm. Imagine if you don't know if you have a negative cycle or not, if you have a negative edge or not. In that case, you just can't apply Dijkstra. Dijkstra has its constraint that you have to use positive edge weight and no negative cycles. So in that case, you cannot use Dijkstra. So Bellman-Ford is used when your requirement is more general, when you have no prior knowledge about the graph. So then you use Bellman-Ford. But again, there are algorithms which kind of speeden up the Bellman-Ford algorithm. So yeah, that is Bellman-Ford. So now I'll just get into the time complexity. So initially you just initialize the entire year, that is just order of V. And then this takes the major chunk because there's a loop which is going for V times. And then there's another loop which traverses each and every single edge. So that becomes order of V into E. And then the other one again is a like second order. So eventually you could turn up with a third order time complexity. So that's why the time complexity of Bellman-Ford is order of VE. Okay. I think this was pretty easy as compared to Dijkstra. And yeah, difference is basically that negative edge weight or negative cycle, Bellman-Ford can handle it. And that is a big thing. So, but if you have prior knowledge, then Bellman-Ford, then Dijkstra is a better algorithm if you know that there's no negative edge weight or negative cycle. And another thing is if you have even better idea of the goal, and if you know that only one goal has to be reached, if you know the heuristic, if you can find the heuristic, then the best algorithm is A star. A more general approach is Dijkstra for that, and then the even general approach with negative edge weight and negative cycle is Bellman-Ford. So yeah, these are the two algorithms. I think these are the references. The one which I used was second mostly, MIT's one, Introduction to Algorithms, and there are the NPTEL courses as well. You can go through them. And then there are like these are the other references that would help you if you have any doubts. So yeah, any other question, or else I'll just call sir for the rest of the lecture. So for Dijkstra and A star, you go in a frontier. You keep on expanding the frontier, and you assume that if you expand the frontier, that would be greater than the one which is closer to the frontier. Now, if you have a negative edge weight, somehow if you are expanding the frontier, you are getting to a node which is closer to the one which you expanded earlier. So the Dijkstra fails because of that. So Dijkstra, the kind of the proof of Dijkstra is based upon that there is no negative edge weight. So if you use Dijkstra with the negative edge weight, basically the correctness of algorithm goes away. A star is also work. A star is kind of a very specific version of Dijkstra. So yeah, it's an informed version of Dijkstra. Yeah. Any other question? If not, then I'll just call sir. Okay. Okay. Thank you, everyone. I'll just stop sharing over here. And